Yeah, let me start by thanking the organizers for inviting me to this conference. Unfortunately, it's only virtual, but anyway, we'll make do. And so today I'm going to talk about, an old subject, but I'll, introduce the subtleties and a new way of looking at things, which will solve some of the problems that we will discuss. Please stop me, whenever needed, because this may be familiar terrain to some of you, but not so familiar perhaps to some others. Okay, so let me start. So in the last few decades, we have found that space-time and geometry have emerged as dual descriptions to matrix-valued field theory. I'll tell you a couple of examples of that. So it is expected that a smooth continuum results if one takes a suitable large n limit where n is the dimension of the matrix. So this is the expectation. We'll see, what subtleties can arise. So in this talk, we'll revisit this issue in some of these examples. We'll explore some subtleties of the large n limit and discuss a way to deal with them. So I have not been very careful about being exhaustive about references, but I will mention as many references as come to my mind as we go along. Okay, so one example of such emergent space-time and geometry, of course, is the ADS-CFT, where gauge invariant operators of SU and Young-Mills fields are supposed to describe bulk fields in the large n limit. To bring out possible subtleties of this limit, however, we will first describe a simpler example. In fact, we will mainly describe this simple example, which in fact predated ADS-CFT. So that's the duality between C equal to 1 matrix model and two-dimensional string theory. So what's a C equal to 1 matrix model? So simply stated, it is a theory of n by n matrices which were functions of time. So there's only one coordinate, that's time. As against in Young-Mills theory, you have matrix fields which are functions of time and space. So here it's only time, and the action looks like this. That is the trace of m dot square minus v of m. And in the particular case of C equal to 1 matrix model, V of m is taken to be minus m square with a suitable cutoff, which makes sense of such a potential. Okay, so the main interest in this problem is in what is called the singlet sector, which is the sector described by the eigenvalues of this matrix. Okay, so let me call this eigenvalues lambda I or t. Okay, so where I runs from 1 to n. Now, for reasons which
Hermitian matrix only, right?
Yes. So for reasons which I don't have time to get into, these eigenvalues, they behave like fermions. Okay, so it's not difficult, but it will just take some more time. So if somebody wants to know how that happens, I can explain that during the discussion time. So anyway, so these eigenvalues become like fermions. So the matrix model in its singlet sector is equivalent to n free fermions with coordinates lambda I of t, and they are in a potential. So it's a free non-interacting fermion. So the full Hamiltonian is the sum of single particle Hamiltonians, and the potential is the same as minus lambda square. Okay, whatever the potential is. So this does not only apply, many of the remarks that I make do not require this particular potential or the C equal to 1 matrix model per se, but any matrix quantum mechanics of this sort. Okay, can you guys see my cursor? I'm not sure.
Yes.
Okay. Good. So it's a non-interacting problem of n free fermions. Okay. So the first thing that one introduces in order to get going, in order to sort of get to observables which look familiar, the first thing that one looks at is the density variable. Okay, the density variable is a counting function defined as such. Rho lambda of t, measures how many eigenvalues there are at some time t between lambda and lambda plus delta lambda. So rho lambda delta lambda counts that. Okay, to be precise, is given by sum of delta functions. Now, so this matrix quantum mechanics is supposed to be dual to two-dimensional string theory. And roughly speaking, the way it goes is that this rho lambda of t from its dynamics. So first of all, you have to write this dynamics of the eigenvalues in terms of rho lambda of t. So this thing can be done. This is called the collective. There's a density theory or the collective variable theory. This was, discussed directly from the matrix model to this density variable by Das and Jivicki. And so you can write this theory in terms of the density variable. Okay. Now it turns out that the density variable has some background values. Okay. But you can look at fluctuations around that background. I have called it delta rho of lambda t, and that maps to the two-dimensional string theory boson. So two-dimensional string theory, because it's in two dimensions, metric and various other string fields, they just get frozen. And the only dynamical content of two-dimensional string theory is a massless scalar field, which is by misnomer, it's called the tachyon. So it's a massless scalar field. So this delta rho lambda t is supposed to be dual to this massless scalar field, okay, in which you have to do a coordinate transformation in space. Okay, the coordinate transformation is as follows. Okay, this is the coordinate transformation that you do, where mu is a constant, which is a chemical potential. Okay, so we will come to that more detail. But there is an explicit map between fluctuations of the density variable and the massless scalar field in two dimensions. Okay, so this is what I said. Now there are many quantities which have been computed to verify this duality, and so in the large N limit, the two sides agree. With regard to many quantities. So there are nice reviews of this subject by Ginsberg and Klebanov, and there are S-matrix calculations which are some of the main things that have been computed. S-matrices, in a topologically trivial sector, as well as in the presence of interactions. As well as in the presence of instantons and so on. So these calculations have started right from 1990s to even now. So there are beautiful papers by Shi-Yin and Ashok Sen in doing this S-matrix calculation. So there are a large number of agreements. But what I'm going to say here is that, however, there are several reasons why such a duality cannot be exact for any finite value of n, however large. Okay, in the following, many of our statements, okay, this is something that I have said, that many of my statements will work for matrix quantum mechanics in general and not necessarily only for the C=1 matrix. Okay, what are the problems? What are the problems with the density variable description of a matrix quantum mechanics? So one is that this rho of lambda t, the density variable, has to satisfy. There's some noise, construction noise going on upstairs. Do you guys hear it?
Not to me.
No, it's very mild, Gautam. No, not a problem.
Yeah, it's like a thunder to my ears, but fortunately it's not so. Okay, so this rho lambda of t has some strange constraints. So it's a very weird function. So far as its functional dependence on lambda goes. So I'll explain where that comes from. So this actually comes from constraints imposed by trace identities. Okay, so what are trace identities? So this follows from the Cayley-Hamilton theorem, which says that if you have a single matrix M, so here I'm talking about any particular given time t. So there, all matrices or all single traces of powers which are higher than capital N, okay, they are not independent. They are actually related to lower traces with the powers going up to N. And this simply follows from the fact that it is enough to determine all n eigenvalues from the first n traces, hence higher traces cannot be independent. So here's an example, let me give you that. So for example, for n equal to 2, trace of m cube, okay, is a polynomial in terms of trace m and trace m squared, like so. It follows from the simple fact that lambda 1 cube plus lambda 2 cube is can be written in terms of products of lambda 1 plus lambda 2 times lambda 1 square plus lambda 2 square and lambda 1 plus lambda 2 whole cube. Okay, so trace m and trace m square are the only things that are independent for n equal to 2, and similar statements can be easily obtained for arbitrary capital N. So however large they are, there are always these identities. So this constraint, this particular constraint, okay, how does it look in terms of the rho variable? Now trace m cube, which is sum over all sum over cubes of all lambdas, okay, that by definition becomes the third moment of rho, okay, like so. And then the first moment is like this. The first moment is like this, and so on and so forth. So you can see that you can very easily translate this constraint, this trace constraint, in terms of the momentum variable. So it's some kind of horrible nonlinear constraint which rho of lambda must satisfy at any given time t. So therefore, if we wish to write this matrix path integral in terms of a density path integral, and eventually, what that would mean for c equal to 1 is in terms of the two-dimensional tachyon path integral, that is the string path integral, we must include these constraints in the measure and hope that they go away in the n going to infinity limit. Okay, so there's a context called a C equal to 0 matrix model where we deal with directly only the matrix integrals and not matrix quantum mechanics. There you can ask many of these questions somewhat more simply and exactly, and how these things go away in the n going to infinity limit are still not worked out in the literature. So that's something that we are working on.
So Gautam, do these constraints kick in at order 1 by n? I mean, do we know if they kick in at 1 by n or 1 by n square, at what order they?
Yeah, so the Cayley-Hamilton theorem has coefficients which seem to go down, with n as you go to higher and higher values of n. But if you look at particular quantities like the thermal partition function and whatnot, it's not it's not easy to prove how the large n limit can be taken, or how you can deal with these corrections coming from the trace identities simply as 1 upon n effects.
Oh, I see.
Yeah. So that's what your question is, and that's what we are trying to prove. But surprisingly, even with an old subject like this, it's not entirely known yet.
Okay. Nice. Thanks.
Okay, so now so that was problem one, that is the trace identities. So they impose constraints on the density variable. Now the other problem, so now we are into problem two. So I'll mention 4 problems just to say what we are going to do. So we are going to mention 4 problems with this density variable, and we are going to propose a solution based on earlier work, which will solve all these 4 problems. Okay, but of course the resultant.
So how does this problem one producing constraints on tachyon field?
I'm sorry.
The problem one, the trace identity, how it is producing constraint on the tachyon field.
Oh yeah. So the thing is that there is a particular map which maps this rho of lambda t to this t of xt. Okay, there are some coordinate transformations that you have to do, etc. So you can write this constraint then in terms of the tachyon field. Of course, that does not make sense because the tachyon field, which is defined by the string theory, string target space theory, does not have any constraint. So the string theory path integral has an unconstrained path integral in terms of this t of xt. Okay, but now you have this constraint. So the idea here is that it should go away somehow in some way in going to infinity limit, so that you recover an unconstrained path integral in terms of the scalar field, tachyon field of the massless scalar field of the 2-dimensional string theory. So the string theory path integral does not have any constraint. Matrix path integral written in terms of densities have constraints, and the point is how do these constraints go away? Okay, that's the. Did I answer the question?
Yeah, thank you.
All right. So now the thing is that, the other problem, perhaps the even more fundamental problem, again related to finite n, meaning finite n, but however large, is the following: that rho of lambda t does not correspond to standard bosonic field which satisfies a Heisenberg algebra. Rho lambda t and its conjugate field, which is usually called pi lambda t, they do not satisfy Heisenberg algebra, meaning the algebra like this. Okay, let me explain. Rho lambda, the way I have defined it, namely here, this is how I have defined it. But it's easy to show that this is the density of the eigenvalues, but the density of the eigenvalues is simply the density of fermions, because the eigenvalues are the fermions. So therefore, rho of lambda is simply the fermion density. Okay, rho of lambda is psi dagger lambda, psi lambda. Okay. Now recall that for relativistic fermions in 1 dimension, massless relativistic fermions in 1 dimension, there's a standard bosonization, which is the simplest version of the Coleman-Mandelstam bosonization that is used in, let's say, string worldsheet construction, etc. That is given in terms of 2 flavors of fermions, psi 1 and psi 2, and one forms complex combinations of them. And using the right movers, you can construct the holomorphic derivative of the scalar field as like this. So what I'm trying to say is that if you have 2 flavors of fermions, then you can construct a scalar field whose holomorphic derivative is given by psi dagger z psi z, and the anti-holomorphic derivative is given in terms of the psi bar dagger psi bar. Okay, so that's the well-known construction. And if you do a mode expansion of the psi dagger psi, then you get the modes of the boson are given by this. Modes of this derivative of the boson are given by this. And then you can show explicitly that an commutator AP dagger is actually n times delta n comma p. This n essentially comes from the fact that there is a derivative that has gone into defining the mode expansion of A. Okay, so this is the standard bosonic algebra, commutation algebra, and this does not work when you have non-relativistic fermions with a finite n and a finite Fermi C. Why does it happen? So let me just say without detail at the moment. In proving this, what are we going to do? What are we doing? We have some psi dagger psi here, okay, and we have some psi dagger psi here. Okay, so it's a psi dagger psi, commutator psi dagger psi. Okay, that, so let me tell you how the algebra of fermion bilinears generally goes. It goes like this. Okay, if you have psi dagger m psi n, call it WMN, then WMN WPQ has some algebra. It's a Lie algebra looking thing in which you have W's also on the right hand side. Okay. Now what happens is that in constructing the A's, okay, you're supposed to have a sum. There's a sum over this index m. Okay. So when you do this kind of a commutator, then you have to have a sum over the first term and you have to have a sum over the second term. Then actually what happens is that by a change of dummy variables, okay, the sum over the first term and the sum over the second term, that just goes away. Okay, for any n not equal to p, it just goes away. And for n equal to p, there are some finite number of terms that remain, which become C numbers by the by the constraint that the the total charge of the system is constant, and and that just becomes a C number. Okay, and so now this change of dummy variable in the summation, in this summation, okay, there's a change of dummy variable that I want to do. Okay, there's a shift of m. Now that works only if the upper limit of m is infinity. Okay. Now, if you have non-relativistic fermions, then the psi1 and psi2, they appear actually like from the particle states and the whole states. Okay, and therefore, because the whole states are finite in number, right? They number up to capital N. So this mode sum for the psi2, okay, it goes only up to a finite upper cutoff. Therefore, a shift of the summation variable is not allowed. Okay, so you are left with some psi dagger psi even on the right hand side, and you don't have a closed algebra. Okay, so the modes of this row of lambda do not have a closed algebra if you have non-relativistic fermions. If you have a finite number of fermions, that is to say a finite depth of the Fermi C, that spoils this Heisenberg algebra. What do you have? So what you have is that there is a closed operator algebra of fermion bilinears that is called the W infinity algebra. This is a certain basis of the W infinity algebra that is closed. There are alternative bases of this algebra, like so. This is written in terms of the position variables, and or UXP. This is the, which is some integral transform of this phi xy. This is called the Wigner distribution or the phase space density operator. Okay, now, so although the position space density operator does not close onto itself under operator commutation relation, the phase space density operator does. Okay, and so therefore, you can have some version of non-abelian bosonization of the non-relativistic fermion system in terms of the phase space density operator. However, it's not very convenient to work in terms. I mean, you can derive several nice results in terms of this, in particular, what is called the droplet picture, and so on, in the large n limit. But however, this phase space density operator actually satisfies the quadratic constraint coming from the fact that we are working on a fixed number fermion number sector. Okay, so there is a quadratic constraint which you can write down in terms of Moyle products of U. So U Moyle product U is equal to U. That's what you get, which comes essentially from this phi equal to phi. So this is some subject which is quite fascinating. This also has the, is related to how SU and algebra are, represented in terms of free fermions and so on. But let me not get into that. Okay, so this does not quite solve our problem, but it gives us a certain set of observables which have a closed algebra, and yeah. But as I said, these are not independent variables because they satisfy quadratic constraints. Okay, so we are still, sort of facing constraints. Problem number 3. There's a problem with particle interpretation. What does that mean? So remember that the moments of rho are given by single trace operators. Okay, let me call them OL. So trace of m to the power L is rho OL. Now, correlators of these do not have a good large n limit, even when L is much less than 1. L over n is L is much less than n. So L over n goes to 0 in the large n limit. So let me give you some exact. So here I have not bothered to write the T1, T2, T3, etc. dependencies, or so I have just written here how the n counting goes. I have just written the dependence on the the powers of the single trace operators L1, L2, L3, and n. So the result is that is square root of L1, L2, L3 divided by n, where I have divided, so I have normalized this correlator by dividing this thing by the norms of these operators. The norms of these operators are given by square roots of the 2-point function. Now, clearly, as long as L1, L2, L3 are all of order 1, and that is to say, when you take a large n limit, they do not participate. They stay, of order 1. In that case, of course, there is a good large n limit, namely 0, which in fact shows that if you construct a state made out of OL2, OL3 acting on the Fermi vacuum, that is approximately orthogonal to the state that is constructed by OL1 acting on the Fermi vacuum. So that gives you a sort of Fock space interpretation of single trace operators as particle states. So single trace operators. So normally you would like to think of the single, because of the sort of purported relation between rho of lambda and the scalar field. Okay, so you would expect that the single traces should correspond to 1 particle states, double traces should correspond to 2 particle states, etc. And if this quantity goes to 0, then this approximate orthogonality between 1 particle states and 2 particle states works out. However, you can see already here that if Li are of order n to the power 2 by 3 or more, then this object actually can stay constant or even diverge. So as a result, the particle interpretation of single trace states does not work. Okay, so this is problem number 3. And problem number 4, this is the most recent thing that we are working on at the moment. and we got some resolution of the problem already. Let me tell you what the problem is. So the entanglement entropy of the matrix model, which is equivalently the entanglement entropy of the fermion field theory, described by psi lambda t. So let's talk about that. So by standard methods, so this is in a very recent paper last year, Shumit Das and collaborators have derived the following formula for the entanglement entropy of a subregion A, which is given by the interval lambda 1 to lambda 2 in the spatial direction of this fermion field theory, with respect to the complement set in the Fermi ground state. Okay, so the idea is to compute the entanglement entropy of this interval in the ground state of the fermion theory, which is the field Fermi C. The result is the following. Okay, so this is some I don't have time to get into the details of how this goes. This in fact uses some of this technology given by the Wigner phase space distribution, etc. But then final result is that it's given by 1/3 log lambda 2 minus lambda 1 times the PF of lambda naught, where lambda naught is the midpoint of lambda 1 and lambda 2, and PF of lambda is the Fermi momentum, okay, at the point lambda. So in the presence of a potential, the Fermi momentum is not a constant, but it's a lambda dependent thing given by this, and this is the formula. Now suppose that, so for simplicity, let me first consider the case of zero potential. So for fermions in a box of length L, PF of lambda is simply proportional to n over L, right? This just follows from the fact that the momenta of the fermions in a box of length L are quantized in units of 1 upon L, and if you have a filling going from 1 to n, then the Fermi momentum would be given by n upon L. All right. So with this, you apply this formula to this master formula here, and what you get is that it is entanglement entropy is given by 1/3 log lambda 2 minus lambda 1 divided by epsilon. Okay, where epsilon is just the inverse of the PF. I have just written it in this fashion, suggestive fashion, and epsilon is just the inverse of PF, which is L upon n. This is very interesting because this agrees with the Calabrese-Cardy formula for massless scalars, okay, with a UV cutoff, which is given by epsilon. Okay, so that's a lattice cutoff. Lattice cutoff as the L upon n, or the UV momentum cutoff, which is the inverse of that, and that's n upon n. So it seems that so remember that when one does the standard entanglement entropy calculation in an interval lambda 2 minus lambda 1, this is what you get, lambda 2 minus lambda 1 divided by epsilon. That epsilon is really the UV cutoff of the theory. That cutoff had no business being related to n. Okay, this is some arbitrary cutoff. Whatever the cutoff is, your entanglement entropy will depend on that. Okay, that is the idea. But here it seems that the fermion entanglement entropy suggests that it is a bosonic theory in which there is an upper momentum cutoff given by n upon L, or a lattice cutoff which is L upon L. Okay, so it appears that the fermion number n is transformed to a UV cutoff for the bosons. Okay, this is completely new. Okay, this is not what you would expect. So this boson is clearly not the standard boson like a tachyon or massless scalar field, which is not supposed to know about this n. Okay, so what bosons are these? Okay, this is a question that we would we ask ourselves, and this is something that we would solve. Okay, let me go to a special case of this problem, which I call problem 4a. So in case of c equal to 1, this formula, you can compute for the c equal to 1, you can put the inverse square potential, etc., do that calculation. And what you will find is that this formula, the fermionic entanglement entropy formula, becomes this. Okay, is 1/3, again 1/3 log x2 minus x1 divided by gs of x0, where once again x0 is the midpoint of x2 and x1, and gsx is this quantity. Okay, this is some position dependent coupling constant that appears in the interaction part of the tachyon theory, which I have not discussed with you so far. But the important thing here is not the x-dependent part, but the n-dependent part here. Okay, so gs of x is given by 1 upon mu n. Okay, where mu is the chemical potential, mu is the Fermi surface counted from the maximum of the potential. Okay, so that's what mu is. And in defining the c equal to 1 critical theory, you take double scaling, the so-called double scaling limit, in which n goes to infinity and mu goes to 0. So remember from standard physics that near a maximum of a potential, the energy level density goes to infinity. So you can hold infinite number of energy levels very near the hilltop. So therefore, this does make sense that you go to n equal to n going to infinity. So you pack up more and more fermions here, and then your mu is driven to smaller and smaller values. So you do that, and then so you hold mu times n fixed in the large n limit, and that is identified by independent reasoning to be the string coupling constant. So 1 upon n gs. So therefore, in case of c equal to 1 matrix model, the entanglement entropy formula can be written, thought of in 2 different ways. One is a similar expression like what we found for the, so look at the second expression. Okay, the second expression is like this thing here, lambda 2 minus lambda 1 divided by epsilon, where epsilon was L upon N. Okay. So in other words, here it was lambda 2 minus lambda 1 times N divided by L. So it was important to know. So it's important to note that N appears in the numerator. Okay. So even in case of the C equal to 1 matrix model, N appears in the numerator. Okay. So this suggests that there is a lattice constant which has N in the denominator. Okay. So this is your epsilon. Whatever appears thing, so that is like Ls divided by N. Okay, so I have brought in here the string coupling, the string length that comes as part of the dictionary of between the matrix model and the string theory, and you just have to trust me on that. The cutoff, the normal cutoff in the string theory is some string length called Ls, and what this formula seems to force us to believe is that the cutoff actually becomes Ls upon N. Look at it here. Okay, so it's x2 minus x1 divided by Ls by N. Okay, the other way of writing it, where one uses the double scaling, is the following: that it's x2 minus x1 divided by GSLS. Okay, so that point of view says that epsilon is actually given by GSLS and not Ls. Okay, so Ls is the standard cutoff that you would like to use in two-dimensional string theory, but what you get here as coming from the fermion theory is GSLs. Okay, so this is surprising from the two-dimensional string viewpoint because one expects epsilon going as LS. So this is our problem 4a. We will now go on to suggest solutions to these various problems. But before that, let me take a pause to ask if somebody has a question.
So Gautam, the divergence of the correlation function when your L
Yeah.
scale is, I mean, is it possible that there is some non-perturbative exponential factor, like some instanton contribution, which would save the?
It's exactly that we are going to use as a solution.
Okay.
In fact, D-brains will solve the problem for us.
Okay.
So yeah, that is right. Okay, so let me recap. We mentioned 4 problems. Okay, one is a problem coming from trace identities. Okay, that says that rho of lambda t is a constraint function. Okay, the other thing that rho of lambda t did not have the correct commutation relation. Okay, these do not have the correct bosonic commutation relation. Problem number 3 is that the single trace operators did not seem to create Fock space states which could be identified with one particle space. Okay, that was problem 3. And problem 4 is that the entanglement entropy seems to suggest that the bosonic theory, whatever the dual bosonic theory is, it has a UV cutoff going as n. Okay, so that is the first surprise, and in the applied to the context of c equal to 1, which I have called problem 4a. There it says that the cutoff, the lattice cutoff, seems to be excuse me, GSLS rather than so that also again sort of smells like D-brains, and we will see what we can say about that.
So
all right.
Sorry, this problem 4a is because there's no independent string theory computation for SA. It's a puzzle in the sense that we expect LS, but we didn't have any. Obviously, these theories are dual, so we would. There's no.
Yeah.
I mean, there's no tension in that sense. Right?
Yeah, that's a very good point. In fact, you might want to have an independent calculation, independent string worldsheet calculation of this object, and see what you actually get.
Yes.
Okay? So I mean that's a very important thing. What I'm saying is from the point of view of the effective target space field theory, namely that I'm thinking of the two-dimensional string theory as the field theory of effective field theory of the target space, which just becomes a field theory of tachyons.
Yes.
Okay, I should have said this before correctly. So the tachyon field you would expect that behaves like a free field. Ignore this, science where it's not which comes from the potential at the end of the lambda space, which is called the Liouville wall. But what you would have expected through the Calabrese-Ricciardi formula applied to just free scalar fields is that it would be log x2 minus x1 divided by epsilon, where epsilon is the appropriate cutoff for the tachyon theory or the two-dimensional string theory.
Yes.
And that appropriate cutoff should have been LS. Okay. Yes. In fact, you can look at the old calculations of S-matrix matching and the new calculations of S-matrix matching, even in the presence of instantons and so on, which talk about non-perturbative matching between string theory. You find LS everywhere.
Okay, I understand. Yeah, right.
You find GSLS. Okay, but here is a calculation which gives you GSLS. Okay, so this is the puzzle.
It's like L-Planck. I mean, one could have thought of LS by N as some L-Planck.
It is like L-Planck, or it is like the D-brain tension, the D-brain length.
Right.
So that is
okay. Thank you.
Yeah. So now the solution. So we'll first tackle problems 1 to 4 and address 4a subsequently. A disclaimer is that we will not be able to say anything conclusive yet about the solution to 4a, but we will have a discussion. Okay. So, but problems 1 to 4 we will solve. Okay, the hint of the solution comes from a situation similar to problem 3, namely that this correlation functions diverging thing. So that problem had appeared in the physics of giant gravitons. Okay, so now I have to take a little bit of a detour. It's not essential. I can go straight to the solution. But let me just say, how am I doing with time? I have 10 minutes for 1 hour. And
yeah, so you started, I think, at 2:30. So you definitely have till 4. So at
okay,
least 4 or 5 more minutes.
Great. So then let me continue slowly. Yeah, please, if anybody has any questions, because some of this could be unfamiliar terrain to some people. I'm not sure, but please do ask questions at any time. Okay, now we are discussing the solution. Okay, so let me, this is a small detour to the physics of giant gravitons. Okay, so the, okay. So what are giant gravitons? So these objects appear in the half BPS sector of the ADS 5 cross S5, which is dual to n equals 4 super angles theory. Okay, so first I'll describe the story of the bulk, and then I'll describe the story of the gauge theory. Okay, what happens in the half BPS sector in both of these things. Okay, so so as you know, the in ADS-CFT, so this is like the canonical example of ADS-CFT in which the geometry is asymptotically ADS5 cross S5, and and that's dual to n equal 4 super angles theory. So in particular, I'll talk about half BPS geometry. What this restriction means effectively is that the geometry is of the form of a rigid S3, the 3-dimensional sphere, as part of ADS5, and another rigid S3 as part of S5. So S5 can be thought of as some kind of a fiber, an S2 kind of fiber over S3, and similarly here rho T, are the fiber directions over S3. So these S3s, they are not deformed further in the half BPS geometry. And so giant gravitons are D3 branes which wrap the second S3. Okay, so it's a D3, therefore it can wrap an S3, and that's what they do. And in the rest of the directions, it looks like a point particle. Okay, so it moves in this coordinates rho T theta phi, and supersymmetry further demands that rho is frozen to be rho equal to 0. So that's the tip of the ADS5 space. And on S5, the motion is essentially on S5 on this theta phi directions. So it is the phi rotates, okay, linearly like this, phi is equal to T, and theta is the latitude of this S2. Okay, the remaining S2 after taking out the S3 of S5. So your D3 brane wraps the S3 and moves along theta equal to theta naught. Okay, at theta equal to theta naught along phi. Now, clearly, the angular momentum here will depend on your choice of theta naught. So the size of the size of this orbit is given by as follows. So it's r squared So if the size is little r, this little r is smaller the higher you go towards North Pole. So there is a formula like this, that if the equator has a radius which is capital R, which is the same as the radius of S5, so the equator has radius R, and the ratio between small r and capital R is just given by this. So R square by capital R square is L upon N. Now, this way this giant graviton, objects were discovered, if not historically, at least logically, is that if you look at the quantum numbers of these giant gravitons, okay, they actually exactly agree with particles, okay, rotating along these particles with the same angular momentum, okay, namely gravitons. Gravitons with the same quantum numbers, but what was found soon enough that the graviton interpretation had a problem, that with increasing L, even when L is greater than square root of GSN, okay, which is a scaled coupling, tooth coupling, then the graviton actually shrinks below the string length. Okay, with increasing angular momentum, the size of the graviton shrinks, and for L, which does not even scale to, it does not even have to scale with N, it just has to scale with GSN, and it shrinks below the string length. So the correct representation was suggested and verified in several subsequent papers by Susskind and Tumbas, and there's a very beautiful paper by Vijay et al. That the correct representation in terms of giant gravitons. Okay, so this is the bulk story. In the bulk, if you want to describe high angular momentum, then you cannot use point-like gravitons, but you rather should use the description in terms of d-branes. Okay, so that is the bulk story. What's the boundary story? The boundary story is that of half BPS sector of n equal to 4 super Young-Mills theory on S3 cross time. Okay. Now the half BPS sector is defined in terms of the following charges. As you know, ADS5 plus S5, the super Young-Mills theory, n equal to 4 super Young-Mills theory, has a conformal group of symmetries that has this maximal, maximal compact subalgebra given in terms of 6 charges. Okay. And namely the energy and 2 angular momenta in ADS and 3 angular momenta in the S5. Okay, so these are part of the SO6 charges. These are the SO4,2 charges. Okay, half BPS basically means that you must put S1, S2, R1, R2 equal to 0. So E and R3 survive, but you must also say that E is equal to J. Okay, so the energy of whatever states are there in this half BPS sector of n equals 4 super Young-Mills theory, energy is the same as angular momentum. Angular momentum meaning S5 angular momentum, which are sometimes called R symmetry charge. Okay, so the so that this restriction actually says that the following fields are they go out of the spectrum, they're simply not there. So mu, there's a gauge field, the fermions, and out of the 6 adjoint scalars, 4 of them go away, and only this pair 5, 5 and 5, 6, they remain, and their dependencies also cannot be on time as well as on sphere. In fact, they cannot have any dependence on the sphere subject to this half BPS condition. Okay, because if they had any dependence on the S3, that would mean that some S1 and S2 would be, that sector would be active. So therefore, you are left with 5, 5 and 5, 6, both as a functions of T alone. But then again, this E equal to J, this condition says that you must construct a complex combination of phi 5 and phi 6, and let's call this matrix as Z, and the half BPS operators are basically single traces and multiple traces of this matrix Z. Okay, and the action governing these Z variable, which you can derive from the original SYM action, as you know. There are the original the literature on giant gravitons describe this all, but there's an absolutely beautiful paper by Suchia and et al. Back in 2004-5 something, which discusses this this matrix model. This is a complex matrix model, but again, so even though it's a complex matrix model, you can go to an eigenvalue description, etc. So you have to just take this thing for a fact. For me, actually, what happens is the following: that it's a complex matrix, so therefore you can upper triangularize it. Okay, and when you have trace of Z to the power Z to some power, it's only the diagonal values that become important. So it is in that sense that even though it's a complex matrix, it actually you can work in terms of just eigenvalues, and this is what the matrix, this is what the action becomes. So the entire super Yang-Mills action just becomes a matrix of quantum mechanics again, like so. Okay, so now, so the point here is that you saw that single traces, which are usually the description of giant gravitons, okay, may not be the right thing now to describe. Description of gravitons. Okay, in the bulk, they are replaced by D branes, which is giant gravitons. So are they are single trace operators, which are supposed to describe gravitons, still the correct description for giant gravitons? Okay, so let me not go into the entire history, but let me say that the resolution was found in a paper by Vijay Balasubramanian and company, that the single trace operators should be replaced by Schur polynomials. Okay, and the reason was in fact exactly the same as in problem 3, which we discussed before, namely that in a giant graviton we are allowing this. Oh, I completely forgot to say that there is a maximum angular momentum. Okay, clearly when this latitude, when this orbit coincides with the equator, right? So in that case, little r by capital R is just 1, and L upon n is also 1. Okay, so the value of the angular momentum goes from 1 to all the way up to capital N. So that's the upper bound for the thing. So we are trying to here describe momenta going all the way up to capital N, and we already found that this problem 3 of ours said that there is a problem in describing such excitations with large values of the angular momentum in terms of single trace operators. Okay, in particular, if L, in particular when L goes to all the way up to N, L and L1 and L2, they go all the way up to N. In this example, however, there's a charge, so therefore, and it's a complex matrix, so I must take OL dagger. One of them has to be taken to be dagger. So OL dagger, OL1, OL2. So where L is equal to L1 plus L2. And in the limit when all the angular momenta go to N, so clearly this is square root of N. And so this says that single traces do not have the particle interpretation. So therefore the single giant graviton states cannot be described by single trace objects. So what are they described by? Okay, now this part is some nice mathematics, nice group theory.
Sorry, but Gautam, even we didn't have to go all the way to n also, right? As you explained before, it could go as n to the two-thirds.
Exactly right. So, but we would like its resolution which would handle even L equal to n.
Yeah, even n. Okay.
Yeah. So let's see how that goes. So now so this is a beautiful paper by Vijay et al. And followed by another beautiful paper by Kohli, Javicki and Ramgulam. Vijay's paper basically says that the Schur polynomials. Okay, I'll explain what Schur polynomials are. Okay, let me first say what a Schur polynomial is. A Schur polynomial depends on two things. One is an irreducible representation of the SU1 group and the SU1 matrix, specific SU1 matrix Z. Okay. So where this is probably not written correctly. So so the point is that it is a trace, it's a character of Z, okay, in the representation, in the irrep R. Okay, I'll explain this thing, what it means. Let's say that I have an irrep given by this Young diagram, okay, in which I have taken this kind of a structure that there are 3 columns, okay, of height 3. There are 4 columns of height 2, and there are 7 columns of height 7. So the proposal is that the character of Z in this representation, okay, gives you the operator, okay, which represents the following collection of giant gravitons, okay, namely R1 giant gravitons at angular momentum 1, R2 giant gravitons at angular momentum 2, R3 giant gravitons at angular momentum 3. So in this example, the numbers are respectively 7, 4, and 3. Okay. So the simplest example are those like the totally antisymmetric tensor representation, let's say, of 2 boxes. Okay. Let's compute the character in this representation of Z. Okay. So I want to find out the trace of Z in this representation. So let's say the fundamental representation is something that I call V. Okay. Let me call the basis of this to be basis of V to be VI, spanned by VI, such that Z acting on VI is diagonalized and it's given by Zi of V. Okay. So that is what. So by the way, many of the things that I'm saying here would work equally well, and in fact, somewhat more simply for Hermitian matrix models. Okay, so this is what it is. And then the good. Now, so this antisymmetric tensor representation is what? It is, if V is my fundamental representation, then it is V wedge V, right? So the basis vectors are Vi wedge Vj. Okay. So the Z, I should have said not V, but Z to the power n. Yeah, so I'll make that thing. Okay, so it's not V to the power n here, it's Z to the power n. Okay, so so Z tensor Z acting on Vi Vj will have okay, let me try to write something here. Hmm. This action has eigenvalues zeta zj like this, and because it's a the basis is vi wedge vj with I less than j, then the set of all eigenvalues in this totally antisymmetric representation is zi zj. These are the eigenvalues for I less than j. So when you sum them all up, it is this sum. Okay, zeta is zj with I less than j, and that of course can be written in terms of the sum of zi whole square and sum of zi square. So that's this. So you can easily find out. So all of these can be beautifully, these have been beautifully explained in the book, for example, of Fulton and Harris, and so on. And so you can also find out in totally symmetric two tensor representation and so on. So so these are, and you can do this for mixed tensors also, partly symmetric, partly like this one. Okay, so these are not difficult exercises to do. Now what I want to say is that the Schur polynomials, how do they act on the Fermi sea? Okay, so in fact it turns out that a Schur polynomial of a totally antisymmetric Schur polynomial of length L produces a hole at depth L. Okay, this is a really cool calculation which you can do. Okay, if I was giving a lecture course, I would have done that on the blackboard here. But so this is what this chi of z is, right? This one, and the field Fermi C is a Slater determinant of this kind. Okay, 1 1 1 1 z1 z2 z3 z4 and so on. Where does this come from? It's a Slater determinant of the so this oops, this theory here, this theory, this actually corresponds to, as I said here, the fermions in these are Landau fermions, 2D fermions, and so for that the eigenfunctions of those fermions are simply monomials of the z's. Okay, that is why the Slater determinant of the field Fermi C are just the lowest degree monomials. Okay, determinant of the lowest degree monomials like this. Now, when you act by Zi Zj, what it does, it still remains a Slater determinant, but it becomes like 1 Z1 cube, Z1 to the power 4. So Z1 square, okay, a hole has been created at the place of Z1 square. So Z1 square has become Z1 cube, and Z1 cube has become Z1 to the power 4. So that basically has created a hole here. This one. Okay, there's a hole here. So this is what this is what happens, and I don't know whether I'm losing people. There's a lot of math I'm doing here, but is this clear? What sort of?
So Gautam, maybe
Hello?
one small doubt. Yeah, this the action of the Schur polynomial on the state.
Yeah,
It's creating the hole at the depth given by the highest weight. for
that's
the-
right.
That,
That's That's right. That's right. Like in this example, the
Yeah.
A is 2.
yeah,
Yes.
yeah.
Angular momentum is 2. So you have two single giant graviton with angular momentum L is given by an L antisymmetric tensor representation. And that creates, so in this case, in this example, L is equal to 2. Okay.
Yes.
And you can explicitly find that this chi box like that of Z is given by this. So you can just multiply out that combination to the Slater determinant of the field Fermi C. And what you get is a Slater determinant of this excited state in which a hole has been created here. Okay.
I see.
So the top two fermions have simply been kicked up by one step each. Okay, good. So this is
one more question about your question 1, which was about the constraints.
Yeah.
Which was in the fundamental representation, right? These constraints that the trace identities that you had in the.
Yes.
So if you instead of working with the trace as the basis of the characters, if you work with Schur polynomials, I mean, are there constraints?
It will do all kinds of good things. So let me just
Okay. So at this point, can we understand this, that you have changed the basis to the Schur polynomial from the trace?
Yes, 100%.
Thanks.
Let me first tell you how the problem 3 gets solved. Namely, that if you compute the correlator of 3 Schur polynomials, okay, then so here are some examples that I have given. So I'm looking at now chi L dagger, chi L1, chi L2. Okay, where these are Schur polynomials of heights L, L1, and L2. Okay, and because there's a charge in the system, I must take L to be the dagger. So, and L equal to L1 + L2. Okay, so that I do. Then explicitly in a beautiful paper by Kohli, Javiti, and Rangulam, this has been computed. And so here are some examples like this one. Let's say I take L to be N itself. Okay, N itself, and L1 and L2, they just split up the this N in this fashion. N by 2 plus capital L and N by 2 minus capital L. Okay, and I let capital L go all the way from 0 to capital N minus 1. So you'll find that if capital L is equal to 0, then it's n by 2 factorial, n by 2 factorial divided by n factorial. So that goes as exponential e to the power minus n. Okay, that's easy to check. And in the other limit in which this L is n by 2 minus 1, that is to say n1 becomes n minus 1 and L2 becomes 1. In that limit also it decreases as a power law, 1 upon square root of n. So in this entire range, this 3-point function, it just goes to 0. So it says, so more generally, so this is just an example, but more generally, you can show that the single Schur acting on the Fermi C is orthogonal to a double Schur acting on the Fermi C in the larger limit. Okay. So therefore, this is consistent with the interpretation of one particle, two particle states, etc. So this calculation and the proposal that the Schurs should be should describe this high angular momentum state, that solves problem 3, the problem 3 that we had discussed before. So as I said earlier, the result continues to be valid even when the complex matrix is represented by replaced by a Hermitian matrix. It's in fact the calculations are even easier. Okay.
So, Gautam, can I ask, so the e to the minus n is kind of what at least intuitively also we could understood as the instant on overlap, because the action would
exactly. In fact, that is really correct. That is really correct. So this is like a one giant graviton tunneling.
Tunneling, exactly. But this square, then in that light, the 1 by square root n is a bit of a puzzle, or
the square root of n, what it does is that, so if you look at that that limit, it's like one giant graviton gobbling up one graviton. Okay, because L2 is actually equal to 1 in that
Right.
unit. And
Right.
L1 is equal to N.
Okay. So there is a significantly more overlap compared to the previous case.
Yeah. So it's like one giant graviton of N-1 gobbling up one graviton of 1.
Okay.
And that becoming this way.
Right.
So that's perturbative. So
It's
therefore,
perturbative computation. Okay. Thank you. I understand. Yeah. Perfect. I see.
okay, so that's so now problem 1 is also solved. Why is that so? This is the question that Alok you asked just now. The Schur operators chi L exist only for L equal to 1 to N, right? Because the maximum antisymmetric tensor representation that you can have in SU2 is of height N, okay, from the group theory point of view, and of course that also matches the maximum angular momentum for the giant graviton from the bulk point of view, and therefore there are no other chi L's. There is no chi N+1, chi N+2. Those things are simply not there. Okay, and so the Schur polynomials exist only for L equal to 1 to capital N, and they are all independent because they involve only trace of z to the power L for L equal to 1 to capital N, which are all independent anyway. So these guys are basically polynomials of all independent traces. Okay, so in particular they are all independent, but you can also find their independence by calculating orthogonality and so on. So in particular, these are not constrained by any trace identities. So basically, the chi of L has a natural cutoff at L equal to N. So they are independent. So we'll realize this independence of the chi L by constructing their action in terms of independent Heisenberg oscillators below. Okay, we'll find that there are n oscillators, not infinite number of oscillators of boson, but there are n oscillators which represent the action of the Schur polynomials, and in that way, what we will find is that these are actually Heisenberg operators with the correct commutation relation. Okay, so I must hurry up now. We will find that they also solve the problems 2 and 4. Okay, so is it clear now how the various problems are being solved? So first of all, the correlated diverging problem that is solved because the correlators of Schur's behave differently, and the Fox-based interpretation is recovered. And then the trace identities do not even apply because there are no Schur operators of L which is bigger than N. So these are all independent operators. Okay, and we'll also see now how problems 2, which is the bosonic Heisenberg.
Can I ask?
Yes.
So Gautam, I have 2 questions. One is when we rewrite the trace of z to the L's in terms of the Schur, you get coefficients that depend on n, right?
Yes.
So are these coefficients in a large limit to be interpreted as gravitational dressing, G-string related dressing?
That's a good question, but the thing is that each of these gravitons, as I was explaining, that they become they shrink. So it is true when you have products of single traces, many a large product of single traces, then the graviton interpretation is probably correct. But if you have trace of z to the power 100 or trace of z to the power L1 times trace of z to the power L2, where L1 and L2 are both large, then
this is like some Gauss law constraint for gravity for the z to the L operator. If you think of z to the L operator and then imagine that there is some Gauss law for gravity or something.
I'll tell you what the problem with the graviton interpretation becomes. Even multiple graviton is that you can write down the wave function. Okay, trace of z to the power L is some kind of a Kaluza-Klein graviton coming from the S5 sector. Okay, and that goes something like 1 over r to the power L. There is a factor in the wave function which goes as 1 upon r to the power L.
Yes.
Now the thing is that you can check at what point does the size shrink below the string length.
I see.
Okay? Beyond which you cannot do not have the graviton interpretation. So it's tempting to say what you are saying, but rather than really trying to see how it interpolates, the graviton thing interpolates, between the Schur and the single trace, I would rather say that it's, I would rather jump to say that there is a description of wrapped D3 branes in the boundary theory in terms of the Schur polynomials.
Okay.
So,
The second question is, you see this A1 to AN are now are all to be thought of as creation annihilation operators for the single tachyon field.
they are okay. So if you're jumping ahead to C equal to 1, I would probably say that they create D0 branes. Okay, but that's only a conjecture at the moment.
Oh, I see. So why is there an N cutoff on the number of creation operators?
I'll tell you that. So first of all, okay, what I want to claim is that the action of chi L on the field Fermi C is given by AL dagger. Okay, so let me try to write.
Yeah. Okay. Yeah. That is clear. Yeah.
Okay. So therefore, these oscillators are finite in number already, but let me tell you how to construct them. Okay, so let me go to the next step. Yeah, so here's just one little step. Sorry for the mess in the slide. So can you guys see this? Because it's my handwriting.
Yeah.
No problem.
Okay, good. So so that was about a single giant graviton. And I began by saying what the composite giant graviton operator is. It's a Schur. So composite giant graviton, where R1, there are R1 giant gravitons of angular momentum 1, R2, etc., etc. So that corresponds to choosing a representation which has R1 columns of size 1, R2 columns of size 2, etc., etc. Okay, so now you can explicitly compute what happened, just like the little exercise that I did for totally antisymmetric tensor of 2 boxes. What it does to the Fermi C, it creates a hole at depth 2. So the more generally, you can do this computation. You can do this computation. Surprisingly, even Wikipedia has quite a nice description of Schur polynomials in terms of determinants, ratios of Slater determinants. So anyway, using that or using Fulton and Harris or whatever, you can prove the following: that chi R1, R2, R3, Rn applied to the Fermi field Fermi C takes you to a new state with the filling F1, F2, Fn. Let's say the first fermion is at F1, the first energy level filled is F1, the second F2, etc., etc. Where you have a following mapping, okay, given by this equation star. F1 is equal to Rn, and okay, so there's a lot of thing. I would refer you to our paper, but you can find the map. So one of the things that is that must check out is that if all the R's are 0, that is to say you are not doing anything at all, then of course this map should ensure that the filling corresponds to the field Fermi C itself, and that does happen. So if you put all the R's to be equal to 0, then you have F1 equal to 0, F2 equal to 1, F3 equal to 2, etc. That's indeed the field Fermi C. Okay, so that means that the no giant graviton state, okay, corresponds to the field Fermi C. Now it is possible to invent A1, A2, AN, and I'll tell you in the next slide how that is done, which satisfy the Heisenberg relations, and they are finite in number. Okay, they are finite in number, and so then this guy is represented by F1, F2, Fn, and this in the bosonic side, I can construct this A's in such a way that R1 number of giant gravitons of angular momentum 1 is given by A1 dagger to the power R1, then A2 dagger to the power R2, etc., etc. all the way up to thing. And this is, of course, by this is something that by standard convention, I will call them R1, R2, Rn. So the map between F1, the Fi's and the Ri's are given by this. Okay. So this correspondence actually sets up an isomorphism between the fermionic Hilbert space and the bosonic Hilbert space. Okay. So this is once more, in this language, I have shown again that this map between the Fi's and the Ri's ensures that when L is equal to 2, that is to say only R2 is equal to 1, or when there's a single Jahn graviton of length L, then only RL is equal to 1. And you can show that the filling corresponds to skipping this hole, this state, and creating a hole here.
So,
okay.
So here the indices A subscript I, the I will determine the angular momentum.
That's correct.
I's and J's.
That's correct.
Right, okay.
That's correct.
So therefore the capital N cutoff is like the cutoff on the angular momentum.
That's absolutely correct. Okay, so now since I'm at the last minute of my allowed time, so the basic point is that there is an isomorphism between the Hilbert space states and the fermionic states. Therefore, you can kind of back calculate and say what the action of these operators are on the fermionic side. Okay, and therefore on the bosonic side, of course, you know what they are, but the A and A daggers can be constructed as follows. So it's done in 2 steps. So start from some filling here and invent an operator sigma k dagger, okay, which does not do anything to the low down fermions, but if n minus k plus 1 onwards, okay, are all kicked up by step 1. Okay, that's what sigma k dagger is, and similarly sigma k is the other way around. Okay, and then the sigma k and sigma k dagger are related to something that is known in the literature of non-commutative solitons, given by the square root division. And with that, you can show explicitly that this is, AK AL dagger is equal to delta KL, R1, etc., like that, and everything works out. Okay. So, good. Now, so this is something that in a paper with Avinash Nimani and Mikhail, we did quite a while ago. But the new stuff that we found recently is the geometry of these oscillators. So there's a finite number of oscillators. So you can construct, in fact, phi of x, okay, in this fashion by putting, in points on a lattice, let's say of length capital L, and by the usual, mode expansion of lattice bosons, and the fact that there are finite number n of oscillators automatically forces you to have n lattice points here, okay, because the oscillators and the phi's have the same bits of information. So therefore, if there are n number of oscillators, then there should be an n number of x's. So that's the main reason why there are, there's a lattice cutoff given by L upon n that appears, lattice spacing given by L upon n that appears, where this n, remember, is the fermion number. Okay, the fermion number therefore determines the crudeness of the circle. Okay, so the points on this circle, how much coarse graining there is on the circle. So it's some kind of a coarse grained geometry that you can invent. And once you have that, you can define a pi also by the desire that phi pi should be delta. And then you can apply the methods of Cassini-Huerta, Calabrese-Cardy and Herzog and whatnot. And you find that the an interval x1 to x2 on this bosonic circle maps to exactly the same interval in the fermionic theory. That was a surprise, but it does happen. and you get the same entanglement entropy formula with epsilon now given by L upon capital N, where capital N is the fermion. Okay, so that's all. It's not surprising because, of course, the theory has an UV cutoff which is given by N. So why do I? Okay, so there's another possible representation in terms of fuzzy tori and fuzzy spheres, where remember that if I have a finite number of oscillators, so that that's like it's a single particle with finite number of energy levels. Okay, so in a semi-classical representation, energy levels correspond to phase space orbits, but if they stop at some finite point, so that corresponds to like a fuzzy torus. And in fact, in the giant graviton problem, this fuzzy torus actually in the ADS geometry it maps to a fuzzy sphere. So this is some story which is easy, but I don't have time to go into that. The dynamics is a little harder. That what is the Hamiltonian in terms of the bosonic variables, but it can be explicitly done, and we have done that. It's complicated, but here I have taken a particularly simple case of the case of no potential, okay, which does not have the Fermi momentum factor there. Okay, now what if there is a potential? So there's a non-zero potential. There you have to work a little harder. You have to put some non-uniform lattice spacing on this bosonic circle, given by essentially a metric which is like this: minus dt square plus gamma square x dx square. In 1D, of course, this is just a coordinate transformation, and you have to choose this gamma of x to be the Fermi momentum of x. Okay, why?
Sorry, shouldn't you be using different mode functions when you have a potential? I mean, rather than e to the ikx, why are you changing the metric?
That's a good point. The thing here is that what I know is about only the oscillators. The oscillators are the ones that come from my map. Okay?
Yes.
What I do, how I construct my real space is pretty much up to me.
Yes.
I could, in principle, have done those.
Actually, that's true. Sorry, I mean, you are right. I think, and meaning you can take at least for some kind of potentials, you can always rewrite the potential term as coming from the derivative. You can transform it into the metric, into a one-dimensional metric. I think maybe that's what is happening here.
This coordinate transformation perhaps has to do with the coordinate transformation that one does in WKB, where one goes from the original coordinate to the time of flight variable.
Okay, yeah, exactly, something similar. Yeah,
we have not been able to completely, pin that down.
So I mean,
okay.
Thanks.
Let me just finish. So now we are. Therefore, with this trick, we can derive with our bosons placed on a circle like this, even the entanglement entropy of the fermions in the presence of a potential. And here, back to problem 4a, which is the problem of this GSLS. So, I mean, it's just a sort of small discussion to say that in terms of this kind of bosonization, using a metric which is gamma of x, which is sin square x, and epsilon equal to GSLS, we reproduce the C equal to 1 entanglement entropy. Note that epsilon equal to GSLS appears. Okay, so the boson in question here does not seem to be the string theory field. Presumably it's a D-brane, but more confirmation is needed. And alternatively, this is another suggestion. So this D-brane possibility has been suggested to me also by Ashok. And here's another possibility here is that since it's all within the log, then can the log GS perhaps appear as like a partition function plus some concentrated curvature, which come in the calculation of entanglement entropy. And there is a paper which Onkar showed me of Juan Malvicena, where factors like this appear. So all this is work in progress. So let me conclude. So we showed that problems with standard showed problems with the standard bosonization, 4 problems. We show that all these problems can be solved by using an exact bosonization of n non-interacting, non-relativistic fermions. The real space bosons are constructed on a lattice circle. Alternatively, they can be understood in terms of fuzzy phase spaces. The entanglement entropy of C equal to 1 matrix model can be explained in terms of such a bosonic theory, which differs from the 2D string. That's all we can say from here, that which seems to differ from the, I should say, it seems to differ from the 2D string. And it is important to study how these observations apply to more general instances of holography, by which I mean that the stringy exclusion principle coming from finite n, they are there in all other all instances of ADS-CFT as well. So and some of these issues do appear, and are there some similar techniques that one can solve there. Thank you. Thanks a lot. Sorry for going over.
Yeah, no problem at all. Thanks a lot for this very engaging talk. More questions?
Gautam, I had a question about problem 1.
Yeah.
Initially, I thought the thing was when we worked with the usual single trace constraints. And
Yes.
then you showed it right in the beginning that in the large n limit, the dictionary between the delta rho and t, that would imply there is some constraint in 2D string theory, but of course there is no such constraint, and that was the puzzle, right? So this was, now the fact that the Schur polynomials have no constraint, so what does it mean that is the dictionary between the string theory and the matrix model, which is 2 at infinite n?
Good point. Now, I don't believe that these oscillators that I have, they are the oscillators of the tachyon. Okay.
I see.
They are the oscillators of something, or maybe they are related to the tachyon in some way, but it's not clear. Because there are a finite number of oscillators. Okay, this is the reason why if you try to impose a trace identity, they all become trivialized. Okay, in terms of the oscillators, everything is automatically valid. But the point is that there are a finite number of them. So clearly the string theory tachyon cannot be constructed like I have constructed this lattice boson here. Okay. Now, like in the giant graviton story, there is a reason why the D branes, it is the D branes that are described by this one. And there is a string exclusion principle, principle obvious because the maximum size is the equator.
Yes.
But what I have been trying to think through is whether the D0 branes, which are, one incarnation of the C equal to 1 matrix model, whether there is a natural, such cutoff for in the D0 brane interpretation.
Or could there be like a string bit model because you're going away from infinite n on the string theory side? I mean, the dictionary between some string bits and the Schur polynomial.
But why should the number of string bits be the same as the fermion?
Yeah, that's true. Yeah.
So in case of the giant gravitons, what happens was the fermion number became the, I mean, that's always the case. Fermion number is the rank of the matrix.
Yes.
Dimension of the matrix, and the that became so for giant gravitons, the story just nicely sits together very nicely, but
correct.
equal to 1, I have to find somehow why this string exclusion comes for this.
Gautam, Ashok has a paper where he computes the W infinity charges of the D0 brane. And similarly, he also computes the W infinity charges of the tachyon modes. And if the Schur polynomials, using those Schur polynomials, those creation operators, if you can compute the W infinity charges, that will be a handle on identifying what is the corresponding thing.
No, that's a good thought.
All right,
That's
okay.
it.
Thank you.
Yeah, I will certainly have a look at that. Yeah, can you send me the yeah, I think I probably
It is.
know what.
I think it is. I think the paper is called W infinity charges. It is
Yeah,
usually
yeah.
string field theory, though.
Yeah.
But I don't think we need to do that. The answer is written somewhat explicitly, so I think one can use it directly. I think that is the point. Yeah, that's.
Yeah, we can discuss this.
Yeah. Okay, sure.
Okay.
Okay, any more
Sorry,
questions?
I have one more question / comment. So you see,
Yeah.
the cutoff on the modes is sort of natural once you think of gravitational back reaction. If you have too many modes or too large momentum, then the background will change for a given G Newton in a certain way, right?
Mhm.
I mean, once you do the gravitational back reaction. So
That's another very important, a very interesting question. That's the so. This
So
is
it is
about,
like these algebras that these people are talking about, this, what type 3 for Neumann or whatever. What you do is you have to dress your creation annihilation operators with some gravitational Wilson lines. And I'm not really sure if that is a kind of way to say that there will be a truncation of the number of modes. But you see, if the energy gets too much, then it's no longer flat space background. And it's no longer the same string theory.
yeah. So the
Sorry, but here in the I thought the puzzle at least 4A was that the entire entropy of string is already finite. I mean, it's already there is already a LS cutoff, right? I thought the question was not why the type 2, type 3 is about the entire entropy is finite. Or
No, sorry. No, that's not what I agree. I think I said it wrongly. But I think what I'm trying to say is that the cutoff on the number of modes. You see, this this Bekenstein bound on the number of degrees of freedom in a given region, right?
Yes.
It smacks of that type.
Okay. I see.
Quantum gravity kind of bound.
Yes.
You pack too much, you're changing, like you're introducing black holes.
Okay.
And those are not creation operators of any kind. So if you want to, in the perturbation, if you want to do perturbative physics, you cannot pack too many degrees of freedom. So therefore, there is an n cutoff on the modes also. I mean, even for a free scalar field theory, I mean, in any number of dimensions, you would imagine that you cannot go to too high a momentum. The creation operator should be truncated, and that the momentum cutoff will depend on G Newton, of course, which is G string in this problem.
Yeah. So by the way, so one can try to do this for LLM, where the back reactions are explicitly taken into account. So the LLM giant gravitons, how does this story work? So this is something that I'm looking at.
Oh, nice. Yeah, that's right.
For ADS giant gravitons, the back reaction story is difficult to do. Although some other giant gravitons, like some other D-brane configurations like in Kolchinski-Strassler, those things are known. So there might, there might be something more general in this story.
Right.
What I have found.
Yeah. Thank you. Very nice talk.
Thanks, Bhatta.
Thanks a lot, Gautam. Yeah, very, very nice talk.
Okay, so I'll stop recording.
Yeah.
Maybe.
Okay.
And